two forces, a horizontal force of 45 pounds and another force of 52 pounds, acts on the same object. The angle between these forces is 25 degrees. Find the magnitude and the directional angle from the positive x-axis of the resultant force that acts on the object. So what we're going to do first here is draw a picture. We have 45 pounds, 52 pounds, and 25 degrees. So that's what we're going to start with this one. So here's a nice picture to kind of start us off. There's another thing I should add to this. This down here is my F1. And this up here is my F2. Okay, so now what I'm going to do from here is when I think about that resultant, the resultant would be the sum of these two vectors. So if we think about the parallelogram method, I do this and I do this and then I draw my line. And this line here would be the sum of those two vectors, F1 and F2, which would actually be my resultant. So this line, this vector here would be my resultant. So that's what we're going to do now. So here's the setup here. So now what I'm going to have to do is find this magnitude of this red vector here, which is the resultant, and I'm also going to have to find this angle x. And that's what they were talking about in the problem. That's what we see here. So it says find the magnitude and the directional angle from the positive x-axis of the resultant force. So this is that resultant force, that sum of the angles. So that's where we're at now. So if I think of this as my xy plane here, that means when I think of F1, I would call F1 45i. And I can look at F2 here. Now, in order to deal with F2 in terms of i's and j's, I would have to add a little more to this. So what I mean by that is I can draw a line straight down here. That could be the first thing I can do. And then I can draw another line over here the same way. Let me try to draw a little straighter if I can. There it is. And then if you notice here, I created right triangles both here and down here. Now, if I was thinking about trying to get something in terms of F2, this vector here, so now I'm using just that piece right there to there. And that vector, I could call it V, or I'll just call it V, give it a name. And then this vector here would be my other one. That one I could call U, so U and V. So then what I could do from here is I could actually find this vector down here at the bottom, this vector V and this vector U. So I'll need one more thing here. So this angle here is 25 degrees. And that also means this angle up here is 25 degrees because they're alternate interior angles. So we can look at those two, and those are both 25 degrees. So now if I was trying to find U here, and I was using this 25 degrees and the hypotenuse, which is 52 pounds, then for U, I could get U equaling so I'm just going to call that F2 for now. And that F2 is times, well, hang on, let me set this up completely. I'm kind of jumping ahead a little bit. So if I was thinking of the sine of 25 degrees, that would be the opposite, and the opposite of 25 degrees here would be U. So that would be U over the hypotenuse, which is F2, or 52. But I'm just going to put F2 for now, just so we kind of can see what's going on completely. So then this implies that my U equals F2 sine of 25 degrees. And I can do the same thing using this triangle down here. Instead of using sine here, I would actually use cosine because I want the adjacent over hypotenuse. Now again, keep in mind I'm using this triangle down here instead now. That's why I kind of drew a box when I set this up. And in that similar way, my V then would equal F2 cosine of 25 degrees. And we know F2 is 52 pounds. So this is going to be 52 sine of 25 degrees. And this one equals 52 cosine of 25 degrees. And these approximate to 0.42261 blah blah blah. And the other one 0.90630 blah blah blah. So they just keep going. So those are going to be my U's and V's here. So that's what these vectors here are going to be. Now keep in mind here, since the V goes to the right here, I'm really going to call that, oops, I missed something here. I missed my 52 here. I should say times 52 for both of these. So be careful, I almost missed it. Okay, so anyways, so now when I times that together, my U here is going to be this vector here. So in general, what I would say was that this would be my J here, because my J usually runs up or down. It's usually my Y component. And then this right here would actually be my I. And those are vectors. So just kind of keep that in mind. So when I think of the I vector, my I vector is 1, 0. And my J vector is 0, 1. And if you had physics already, you probably dealt with these already, but if you haven't, that's what they mean. So this is strictly running in the J direction, my U is, and V is strictly running in the I direction, which is in the X direction, I should say. Yeah. So now we have everything we need to set these, to find this resultant force, the magnitude of the resultant force, which we would just call the resultant force, I'm sorry. Yep. So there's our approximations even more of U and V, which are the forces of the IJ forces of my force 2 there. So now what we're going to do is we're actually going to find the resultant. We're going to add these two together. So now for my F1 plus F2, because that's what I'm looking for here, that's going to give me that resultant force. That's going to simply be my 45I, which was my F1, and that was here. Oops. That was here. Okay. And then I'm going to add that to my F2. Now my F2 is going to be the sum of U and V. Okay, so I'm just going to add those two together, and that's going to be these two here that I approximated. Okay, so that's going to be, and there they are, because it's going to be both those together. And then I can add my I components here. This first one is really 45, 0, if I think about it in terms of standard position vector. That's what it would be. So I would really just be adding the 45 with the 47. That's what we're going to do here. Okay, so that's going to be, so there's our resultant force here. So now what we're going to have to do with this is we're going to take the magnitude of that, because that's truly what our force is going to be here. It's the magnitude. It's not the vector itself. So to get that, we're going to have to use Pythagorean theorem. That's the idea. So that's going to be the magnitude of the vector f1 plus f2. And that's going to be, which this results in, and then when I square root, I get approximately 94.71283. Now, if you're a little off, I didn't just square this number here. I took all of it, as much as the calculator gave me for both of these. So be careful with that. So if your number is slightly different, that will be why. It's a rounding error. So that's what I would end up with here. So that would be my resultant force. So now what I would do is I would have to find x here. So that's the first part of my answer here, which would be that answer. Now the next part, I'll need to incorporate to find that x here. I would have to use the tan of x. And usually the tan of theta, when we think of it in general, is equal to y over x. But what we have here is we have the tan of x, and that's going to equal our opposite. I shouldn't say our opposite, I should say our y direction, which would be my u, over my x direction would be my v here. So it would be my u over v of my resultant. So then that would give me my y being this 21.976. So that's going to go on top. And then on the bottom, I'm going to get my v direction there that I used, and that's going to be the x direction that we normally see with the polar. And that's going to be 92.128. And then from here, I'm going to do a tan inverse. And that's because I want to get an x. So I'm going to do x equals the tan inverse of all of that business there. Because I want to find that x. And that'll be my answer for this one. So it's approximately, so it'll be 0.023463 radians. Now remember, be careful of the mode of your calculator. You may have gotten degrees. So that's my second part of the answer there. So those are my two parts here. So now we're done.